Good afternoon and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Kaur, and in today's lecture, Lecture 7, we'll be finishing up some of the material that was in 1.2, the section on limits in our calculus textbook. Just as a reminder, tomorrow quiz 2 is tomorrow at 3:40. That's correct. And it'll be about 10 minutes in length, and then we resume our lecture at 3:50. Perfect. Good to hear that everyone can hear me okay. And yes, excellent. Just as a reminder from our last lecture, we looked at some of the basic properties or rules of limits. We had the sum rule where the limit operator is applied to each of these terms here. So right here we have it applied to f and g. Same thing with the product rule. If we had a multiplication here, that's a dot there. So we apply the limit to each of these. It just is the limit applied to each of the terms. We have a reciprocal rule, which just applies the limit to the denominator. Followed by, we have a constant rule, which is the limit of a constant is itself, and the identity, which is the limit as x goes to x naught of x is just x naught. So that means we have some derivable rules, which means that in the book we could derive it using these basic rules up top, but the extended sum rule means that I can take this limit operator and apply it to each individual term, and I get very similar to what I was doing up above. To all the individual ones, I can take the limit of 1 to all the way up to n. So very similar to this. For two functions, I can do it for n functions. And similarly, I can do it for when there's a product, that if I apply it to each individual function, then I can have the limit of x goes to x naught of f1 of x times the limit as x goes to x naught of x2 all the way up to f of n. And the way that we would get these is just repeated application of the sum rule to get the extended rule, repeated application of the product rule to get the extended rule. The constant multiple rule is a combination of the constant and identity, which just says that I can pull out this constant, because you can think of the constant as a function itself. And so by the extended rule or by the product rule, I can apply it to each of these, and the limit of a constant is just the constant. So I'm just left with the limit as x goes to x naught of f of x. And by applying the reciprocal rule and the product rule, you can actually apply, you get the quotient rule, which is just applying the limit to the top and bottom of the rational function. And lastly, we have the power rule, which is that if I have x to the n, the limit as x goes to x naught, it's just x naught to the n. For n where it's a integer, and if x naught is not equal to 0, that's if n is not positive. Okay. So moving on. Those were just some properties. Now, an important question that we could ask ourselves is the existence of limits, meaning, the limit as x goes to x naught of f at x may not exist. And what I'm going to try to do is show you that for the limit to exist, the behavior in the neighborhood around x naught should be the same. And What do I mean by that? Well, just looking around, kind of around x naught. Let's just use a little bit of an example. So here's an example. I'll draw the function here. So here's a function, my axes here, x and y. And I'll do a dot here. And I'll do an open dot here. Let's make that a little darker. And what I've drawn is the Heaviside function. So it's a kind of a step. So it goes to x equals 0 here, and then it jumps up to 1 and for the rest of the function. So this is the Heaviside function. You don't need to know the name of this, but it's kind of a function that pops up a lot in engineering applications. So we have h of t. Oh, so instead of that, I should put t here, and this is my y equals h of t. And so it's 1 if t is in the domain, or sorry, t is in the interval. So it's a closed bracket from 0 to infinity, round bracket, and 0 if t is less than minus infinity to 0. So what I'm saying is we're going to look around the neighborhood. Kind of around here. So a small neighborhood right around here. So you can kind of think of that as a neighborhood. Neighborhood of x equals 0. So what happens is if we approach x equals 0 from the left-hand side, we see that that value is 0. And we notice that if we approach from the right-hand side, that the value is 1. Now, we have two different behaviors in this neighborhood of x equals 0. And what we need to do is for the limit to exist, the behavior has to be the same. So what I should write then is we have two different behaviors in the neighborhood of x equals 0. Now, some people, in the textbook, we don't get to it, but we'll talk a little bit more. It's trying to be intuitive, but we'll introduce a little bit more notation than what the textbook does. So, for instance, when we're talking about the limit, we start to talk about a one-sided limit. And as we're approaching from the right-hand, or from the left-hand side, so this is the left-hand side, we write the notation, the limit, as x goes to 0. And by 0, we have a left and a right-hand side. So for the left side, we use a minus. So the limit as x goes to 0 from the left-hand side of the Heaviside function. Oh, and maybe I should be using t. The reason for that is because the Heaviside is using t in this. So So approaching it from the left-hand side of the Heaviside function, we get 0. And from the right-hand side, we'll use a plus. So as t goes to 0 and the superscript plus of h of t is equal to 1. So we have two different behaviors. So this is what we have graphically, and this is what we have mathematically. So mathematically, the limit as t approaches from the left-hand side of the Heaviside function is not equal to the limit as t approaches from the right-hand side. And this implies that there's two different behaviors around t equals 0. So this implies that the limit of t approaching 0 of h of t does not exist. Some people will use the shorthand form DNE to stand for does not exist. Okay, so to summarize that, if the limit from the left-hand side, so the limit of the left-hand side does not equal the limit of the right-hand side, then the limit doesn't exist. And then, of course, if you have the limits on the left-hand side and the limit on the right-hand side, they equal the same number, let's say L, then the limit does exist. And that limit is actually equal to L. Okay. Page 3. So let's say we're going to, does a limit over a single hole in a line exist? That's a good question. We'll get to that. Actually, maybe I can answer that right now. So he's asking about a hole. So what he's talking about here is I have a function, I have x and I have y, and I have some function here. Okay. Let's say this is 2 and this is 3. So in this case, I have a hole here. And the limit from the left-hand side is going to 2, so it equals 3. So the limit as x goes to 2 from the left-hand side is equal to 3. And the limit as x goes to 2 from the right-hand side is equal to 3. So these both are equal. So yes, then the limit is 3, even though the function does not exist at that point. Another one. In the case of a function where the values of y are the same, but flipped about the x-axis, would the limit exist? The values of y are the same. I don't quite follow the question. But what you should do is draw me out a picture of what you mean and send it to me by email, and then I will be able to answer that question. But I'm not sure when you say when you're flipping, if you're talking about the inverse function or, but just draw me an example and then we can work through that by email. Okay, so I have an example where I have show that the limit is equal to 0. So we can remember what the absolute value function is, right? It's x if so it stays positive if x is positive, so that's from 0 to infinity, and minus x if x is less than infinity to 0. And so just a quick sketch looks like something like that. So we have to show what it looks like at as the limit's going to 0. So yes, we can see that as we're going from the left-hand side, okay, now we have to apply our, apply our function. And we can just plug in our 0 in this case, so that limit is equal to 0. So we have this on the left-hand side. A tangent or an inverse sine cosine would be examples. Inverse sine cosine. A tangent. I'm wondering if he's, see, this is where I think he's, for instance, like when I'm thinking of, he's asking, I think, let's just simplify this just a little bit. So I have right here, this is a vertical asymptote. And let's say that I have something like this. It's approaching to this vertical asymptote. It's going off to infinity. And let's say that, you know, I want to do, say, like the tan function. Something like that. And, you know, it always kind of repeats. This is going to negative infinity, this is going to a positive infinity. So again, the limit doesn't exist here. Again, they're not going to the same value. Like these are not, it's not defined there. Okay. Yep. Yeah, so in this case, the limit doesn't exist. It has to equal L. And in this case, L has to be a real number, and that real number does not include infinity. So it has to be a finite value. Okay, so this is the left-hand side. And I have the right-hand side. So same idea, the limit as x goes to 0 on the positive side is just x. Subbing in our 0, so we just is equal. So we see that, since the left and right hand limit are equal, well, let's say side, then the limit as x goes to 0 of the absolute function x is equal to 0. Okay. Oh, I better, I thought I had. So we have a definition. We have to understand the idea of continuous, and particularly continuous at a point. Intuitively, we think of a continuous function as a function that I can draw. And now remember, it has to be a function, so it means that it has to be it has to pass the vertical line test. But it means that I need to be able to draw the function without lifting up my pencil. Well, I have a pen, but some drawing instrument. So for instance, that's like a continuous function, but for instance, doing that is not a continuous function, because at that point I have to pick up the nib and place it at a different point. Okay, so this function, or this definition, so what it's saying is that the function f at x is continuous at a number x equals x naught if the limit at f at x as x goes to x naught is equal to the function at x naught. So what that means implicitly is three things. It means that the function has to be defined at x naught. So for instance, this example that we had earlier from our question, this function isn't defined at 2, 3. So it's not defined, so it fails to be continuous at that point. The limit has to exist, which means that if any of these three are violated, then it's not continuous. So it fails this one, so immediately this is discontinuous at this point right here. In this case, this function is also not defined at that point right here along this vertical asymptote. And moreover, the limit doesn't exist because we have it going we have two different behaviors within the neighborhood. And lastly, it has to be defined at that point. So if I wanted to make this one, say, continuous, because this is a straight line here and a straight line here, at least that's what I tried to draw. If you wanted to make it, it's going to the function as it's going to 2 from the left-hand side and the right-hand side, it has to equal, the limit has to equal that at that function. So I have to be able to put that value in at 2. And in this case, it isn't. So if you wanted to make it continuous, you just fill in the hole. Okay, so that brings us to 3 different discontinuities. And then I have the 3 implicitly defined kind of criteria for our continuousness. So I have 3 different kinds of discontinuities. This one is called, well, it's obvious. Well, we call it a jump discontinuity for the obvious kind of idea of it's kind of making a hop or a jump. So this is called a jump discontinuity. And it is defined at x naught. The limit does not exist. And we also see that the limit doesn't exist, so then automatically it fails 3 as well. So we were calling this a whole we were calling this a whole, but I believe they call this something this is called a removable discontinuity. You might hear me say a whole discontinuity. Discontinuity. For the obvious reason. Again, it's a whole. And, oh yes, okay, so yeah, it's not defined here, so it fails 1. The limit does exist, as it goes from the left and the right-hand side. And it fails 3 because it doesn't, x naught doesn't exist, so that fails. Oh, and so then we get this type of discontinuity, and that is called, oh, they called it an infinite discontinuity. So we see that it's going off to infinity around this one, and it's going to minus infinity on the right-hand side. And it's not defined at this x naught. So it's not defined, so it fails 1. The limit doesn't exist because it's going to 2 different numbers. Well, it's not even going to a number, so it fails. And it fails 3 automatically because it's not defined. Okay. Okay, so that was 4, and here's 5. So the textbook's quite informal at this point when dealing with limits involving with infinity. And by that I mean, say, x going to infinity. So for instance, they just say, if I'm looking at 1 over x, and I just start thinking of like really big numbers. So for instance, I start to let x go to infinity. So I have like, you can think of 1/2, and you can think of 1/4, and you can think of 1/8, 16th, 10,000. Each time you're doing that, as you're making x get bigger, the whole fraction goes smaller. So you can see that this is approaching 0. And there's the graph here. It's a reciprocal function. Same thing here. It goes even faster. If I had 1, so it's if I square that, it's 1/4. I have 1/16. 1 over 8 is squared is 64. Dot, dot, dot. It's getting smaller as well. So again, that limit is going to 0. So I have these two kind of pieces of intuitive knowledge. So now how do I handle something like this, where I have 2x plus 1 over 3x plus 1? And their idea is to express it in terms of 1 over x. Because I already know what that limit is, that if I can somehow get it to 1 over x, then I know it goes to 0, and those terms then cancel out. So applying the limit as x goes to infinity on top and bottom. And the other thing is I'm going to apply 1 over x and 1 over x. So again, what I've done is I've multiplied by 1 over 1, and that shouldn't be too concerning for people, because again, I have 1 over x, 1 over x, and I can flip this up because it's a which gives me x over x, which gives me 1. So I haven't done anything. I've multiplied it by essentially 1. Okay. So that we're okay with that. I can distribute that. So 1 over x times 2x gives me just 2, plus 1 over x divided by 3 plus 1 over x. And applying it to each, this is just a constant, so that's just 2. What the nice thing is using a, what we've done up here, which was equal to 0, I know that this goes to 0 and this goes to 0. So I'm just left with 2 over 3. Okay, we have d. We have the limit as x goes to infinity, and I have 5x squared minus 3x plus 2, all divided by x squared plus 1. Now the idea again is I would like to get it in terms of 1 over x, and it'd be also nice to get it in 1 over x squared as well, because I also know what the answer is for that, so that's 0. So what I'm going to do, again, very similar to what I've done previously, I'm going to divide not by 1 over x, but instead 1 over x squared, because I'd like to get rid of these x squareds. So 5x squared minus 3x plus 2, all over the limit as x goes to infinity of 1 over x squared plus 1. So I can start to do a little bit of simplification. So just distributing this 1 over x squared to each of these terms, I have 5x squared gets canceled by the x, or the x squared. So I'm just left with 5 minus, I have x divided by x squared, so I just have a 3 over x here. And lastly, plus 2 over x squared. Going to infinity. And I have x squared over x squared, so that's just 1 plus 1 over x squared. So applying the limit to each of these terms, the limit applied to just 5 is 5 minus, I have, you can think of this as 3 over x as equal to just 3 times 1 over x. So I have 3 times the limit as x goes to infinity of 1 over x plus, same idea here, I have 2 over x squared. So that's 2 times 1 over x squared. So I have 2 times the limit as x goes to infinity of 1 over x squared. So the limit applied to 1 is just 1 plus the limit as x goes to infinity of 1 over x squared. So now that I've done this, I can apply a and b again. So I had 1 over x goes to 0, this 1 over x squared goes to 0, and same thing here, so 0. So I'm just left with that goes to 0, which means that the 3 is multiplied by 0, so that's 0. The 2 is multiplied by 0, so that goes to all 0. So I'm just left with 5 over 1, which is just 5. Now, we could be finding the limit of the limit as, a limit involving infinity from a graph. So for instance here, I have a graph here. This is the black curve here, which is the function. And I have two, I have 2 horizontal lines and 1 vertical line. So in this case, as x goes to minus infinity, we see that it's approaching but not touching this line y equals 2. So in this case, as the limit as x goes to minus infinity, that's 2. And as we go to infinity, so out to the right-hand side, far, far, far out to the right, we see that the behavior of the graph is approaching this y equals minus 3. So that's what it would be for this. Just some terminology then, which I probably have mentioned already now, that these blue lines, these horizontal lines, are called horizontal asymptotes, and the vertical line here is x equals 1 here, is a vertical asymptote. So let's move on to the formal definition of the derivative. If we have a function f at x whose domain contains an open interval, so again, that's the idea of the neighborhood about x naught. So I've drawn this little diagram here. So there's like our x, and I have my x naught, and I have an open interval around it. We say f is differentiable. So that's the term that we're defining here. It's differentiable at x naught when the following limit exists. So again, that means that the limit has to be the same approaching from the left-hand side as the right-hand side. So f prime of x naught is equal to, and we'd seen this before, it's the limit as, it's the change in the delta y over the delta x, and that expands out when we write that. F at x naught plus delta x minus f at x naught all over delta x. Again, that's at a very specific point, x naught. So then we say that at f prime at x naught, it's called the derivative of f at x naught. So this is what we'll be using as our definition. So important, we'll put a box around it. So let's use the definition to find what the derivative is of this function, and then we'll plug in that point 3 to find what the derivative is at x equals 3. So using our definition, now I'm going to, in this case, just let x be arbitrary. So in this case, it's at a very specific point. I'll just do it for every x. So again, just copying down this definition. And then substituting in the values x plus delta x into the function. So it just becomes x plus delta x all squared minus x squared all over delta x. And then we expand that over, well, expanding this, what we get is x squared plus 2x delta x plus delta x squared minus x squared all over delta x. Those cancels because they're the same. So then we're left with 2x delta x plus delta x squared all divided by delta x. Factoring out the delta x, I'm left with 2x plus delta x. So again, those can cancel. So by the sum rule, I can apply my limit rules. So by the I can apply the limit to each term. So I get the limit as delta x goes to 0 of 2x plus the limit as delta x goes to 0 of delta x. So that's just 2x, and this goes to 0. So I'm just left with 2x. So that's my derivative. And I'm still asked to find what f prime of 3 is. So f prime of 3 is equal to 2 times 3, which is 6. Perfect. So we also have Leibniz notation. So if we're given a function y equals f at x, then the derivative f prime can also be written as kind of this idea of an operator. So d by dx. So you can do like d by dx applied to y, or you could do it to f, Or sometimes people will write it all together, so like dy by dx, or df by dx, or sometimes they'll write dfx over dx. These are not fractions, it's an operator. If you want to show that you're evaluating it using Leibniz notation at a specific point, then we write dy by dx, and then we have a vertical bar, and then we write x equals, and then the number. So for instance, I could have y equals x cubed, and we're asked to find what the derivative is at x equals 4. So doing that, I have dy by dx. So I'm going to first find the derivative. So writing out the definition. Okay, and we're going to expand using the Pascal's triangle. Again, we had that little trick where we had it descending, so we had x cubed plus x squared plus x, and then we'll have the delta x's, so we'll have a delta x squared plus delta x cubed. Remember, there's the minus x cubed, or yeah, x cubed that I need to have there. And then I also need the coefficients. So I've written them up here. Here's Pascal's triangle, 1, 1, 2. So this is the third row is what I need because it's a third degree expansion. So it's going to be 1, 3, 3, 1. Divided by x delta x. The x cubed and the minus x cubed cancel out. So what I need to do is I'm all left with terms that have x delta x's in here, so factoring those out, I'm left with 3x squared plus 3x delta x plus delta x cubed. Oops, should be squared. Okay, cancel those out. And then I'm left with 3x squared plus 3x delta x plus delta x squared. Applying the limit to each of these. Which means that this goes to 0, this goes to 0, and we're just left with 3x squared. So that's the derivative. And then lastly, we need to evaluate, because we're asked what it is at x equals 4. So evaluating it at x equals 4 gives me 3 times 4 squared. 3 times 16 gives me 48. Okay, so that is 15 seconds left till the end of my lecture. We didn't get to cover the section in the textbook involving the differentiation of polynomials. So those will not be on the quiz for tomorrow, but you are expected to have done up to section 1.3. If there's any questions, feel free to leave them in the chat. Again, you are welcome to send me an email. You have my email address. And hopefully there's no more questions about the homework, but if there is, again, just an email away. Thanks again, everyone, for tuning in for MAE 113. This was Lecture 7. My name is Richard Kohar, and again, if you have questions, feel free to send me an email. Have a good night, everyone. Take care.